Hi everyone, so in this video we are again going to be talking about systems of inequality, and we are almost getting to maximization now as well. So again, for these examples we are going to graph the system, we are going to find the corner points, and we are going to say if the solution region is bounded or unbounded. So let's go and get started. Biggest difference for these examples is we do have three different ones to graph. So we have all three of these, along with, again, x and y greater than or equal to 0 just means that we're only going to be working in this first quadrant. Alright, so let's go ahead and get to graphing. So first off, we have 2x plus y equals 10. We can subtract 2x from both sides, and we get y equals negative 2x plus 10. So our slope is negative 2 over 1, and our y-intercept is 0, 10. So we go up to 10, and then we go down to over 1, over and over. And then we go ahead and graph a line through it. It is less than or equal to, so I will go ahead and shade below. All right, next one. X plus y equals 8. So we can subtract x from both sides, and we get y equals negative x plus 8. So our slope is negative 1 over 1, and our y-intercept is 0, 8. So let's go ahead and go up to 8, put a point, and we go down 1 over 1, and draw our line through it. All right, again, less than or equal to, so that is below. That's our second one done. All right, last one. 2x plus 3y is equal to 18. Okay, so we are first going to subtract 2x from both sides. So we get 3y equals negative 2x plus 18. Divide both sides by 3, and we get y equals negative 2/3 x plus 6. So we're going to go up to 6 and then go down to right 3 and draw our line through that one as well. Alright, this one is also below. So if I go ahead and shade this one as well, the colors get a little uglier in this case, but we can still see where they're all overlapping. So they're overlapping in this corner region. So this is our solution region. Now we just have to look at the actual corner points. So we have 4 in this case. 1, 2, 3, 4, and I know you can't see that very well, so 1, 2, 3, 4. That's a little better. So those points are 0, 0, 0, 6. Let's see, that's 3, 4, and 5, 0. Lastly, we just want to say if our region is bounded or unbounded. Again, for this one, we can draw a circle around the entire thing, so we consider it bounded. Luckily, for number 6, all of our lines are the exact same lines. The only difference is that this time they're all greater than or equal to. So, we're going to go ahead and graph these same exact lines. So I'm going to go ahead and put them on the screen now. There we go. There are all the lines again. So if we go through them one at a time again, the blue one we're going to shade above. So that's going to be this region up here. The yellow one we are also shading above. And then the red one we are also shading above. Okay, the red does not play as nicely with the blue. So let me see if I can find another color that works a little better. Here we go, this pink seems to be a little bit better. Alright, so again, this one's a little hard to see, so if you want, you can just skip the highlighters altogether. And I will do that just to make it a little more visible. If we want above, and above, the only place with all three colors is this region right here. So if you go outside of this area, you'll see that they only have 2 or less of these colors in any of those sections down there. This region up here, though, does in fact have all the colors. So that's what I'm shading in darker. All right, so with that, we can go ahead and find our corner points. So for B, we are going to have 1, 2, 3, and 4 corner points. Those corner points are at 0, 10, 2, 6, 6, 2, and 9, 0. And for this one, part C, couldn't draw a circle around it because it does go on forever, so it is unbounded. Okay, so we've learned how to do this now. Let's go ahead and see how we use it. So we're actually going to start a problem where we are going to be minimizing and maximizing a function. So first off, let's go through this and see what this problem is actually asking. So minimize and maximize z equals 30x plus 10y means that we are trying to find the x and y values that make z both as small as possible and as large as possible. All right? Subject to these are called constraints. These are rules that are placed on x and y. So if we wanted to make z as big as possible and we didn't have these constraints, we could just say x is, infinity and y is infinity. We could make them ridiculously huge and they could always get bigger and z could always get bigger. These constraints limit that because x and y can't be just anything. X and y have to actually fall within all of these constraints. Right? Now keep in mind we do still have this last one, which on our graph is just going to be, again, the x and y axis, and it says that we're in the first quadrant. But specifically, whenever we start talking about minimizing and maximizing, it specifically means that x and y both need to be positive numbers. And that's going to become a lot more important whenever we get into the word problems for these, because if we are trying to maximize things by asking how many tables do we need to make, well, we couldn't make a negative number of anything. So those are usually going to be there from now on, and it's just saying that both of our values need to be positive. Okay. So before we get to the minimize and maximize part, we're going to do the same thing. We are going to graph all of these. Once we graph them, we are going to shade the region. We're going to find the corner points, and then that's where our new part is going to begin. So let's start by graphing all of these. So I'm going to go ahead and use my same little color scheme that I've been using. So first off, 2x plus 2y equals 4. So we can subtract 2x from both sides. We have 2y equals negative 2x plus 4. And then we can divide both sides by 2. Get y equals negative x plus 2. Cool, so that means we're going to start up 2, go down 1 over 1, and then draw our line through it. Hopefully by now everybody's okay with the slope was negative 1 and the y-intercept was 0, 2. So let's draw this line. And then it is greater than or equal to, so we are going to be shading above. All right, on to the yellow. So we have 6x plus 4y is less than or equal to 36. So we can subtract 6x from both sides. So we got 4y is less than or equal to negative 6x plus 36. Then we can divide both sides by 4. So we get y equals negative 3/2 x plus 9. So we're going to be way up here at 9. We're going to go down 3 over 2. And let's draw the line through that as well. This one is less than or equal to, so that means below. So we're going to go ahead and shade below this line. All right, last one. 2x plus y equals 10. So we are going to subtract 2x from both sides, and we get y equals negative 2x plus 10. So all the way up at 10, and then down to right 1, over and over. Draw our line through it. And this one's also less than or equal to, so I'm just going to go ahead and shade it lightly below it. All right, so our feasible region, or our solution region, is going to be where it's green and has those red stripes. That's where all three of them are overlapping. So that is down to here, over here, along the bottom, because remember, we don't want to go past the axis. Then right here, and down here. And then we can just lightly shade that inside part in. Perfect. So what are our corner points? So our corner points are going to be 0, 2, 0, 9. This one's a little harder to see, but 2, 6 is a corner point. Because even though it just barely changes, there definitely is a corner there. Then 5, 0, and 2, 0. By the way, I should mention that these corner points are not in any specific order other than the order that I happen to see them in. So if you get a list of corner points in a different order than I do, that is no big deal at all. It's going to be perfectly fine. Okay, so now we are going to make a little table. In this table, we are going to have our corner points. Next, we are going to have this function from up here, 30x plus 10y. And lastly, I'm just going to put z right here. Okay, so the corner points we know, so I'm going to go ahead and fill those in. 0, 2, 0, 9, oops, 2, 6, 5, 0, and 2, 0. Now remember, each of these is x comma y, right? So we are going to plug each of those in to the 30x plus 10y. So for the first one, we are going to get 30 times our 0 plus 10 times the 2. Plug that into your calculator, and we would get 20. And we're going to do that again for each corner point. So 30 times 0 plus 10 times 9. And again, plug that into your calculator. You are going to get 90. Next, 30 times 2 plus 10 times 6. Plug that into your calculator. That should be 120. Next, 30 times 5 plus 10 times 0. This is going to get us 150. And then the last one, 30 times 2 plus 10 times 0. That one is going to get us 60. Okay, so we want the minimum and maximum of that function. Luckily, one thing that we do know for certain is that the minimum and maximum has to be a corner point. If it was a random point in the middle, let's say, for example, that our corner point was this point right here in the middle, or let's say our maximum was, well, we could just go up more and get something that was bigger. Or we could go down more and get something that was smaller. The only points that don't have a chance of us going up or down to find something that is bigger or smaller are corner points. So we know that they have to be corner points. So for this first method, we kind of just brute forced it. We found all of the corner points, we plugged them all in, and now all we have to do is look through these values to see which one is the biggest and which one is the smallest. In this case, 20 is the smallest, which would be our minimum, and 150 is the biggest, which would be our maximum. All right, now it does depend on the question and what it asks for, but in general, here's how we're going to write our answers for stuff like this. We would say that this function has a minimum of 20 at the point 0.02. We want both of those things. We want both the minimum and we want the corner point that got us there. Same thing for the maximum. So we would say that we have a maximum of 150 at the point 50. And then we're done with this problem. Now, one thing to note is in the future, for this class, we're going to be focused on the maximum part. And we're going to stop brute forcing it like this because this is a lot of work. And not only is it a lot of work, but what happens if it's not an easy function to graph? What if these lines, don't intersect at nice places? How could we find those corner points then? What would we need to do? That's what we're going to be looking at in the next set of notes, is other methods to do this same idea of getting to that maximum, but without necessarily having to go through all the trouble of graphing every single line and plugging every single one in. All right. With that said, though, that is the end for this set of notes. So thank you for watching.